a blue roof. So in a nutshell, it's really about ponding water on the roof of a flat roof building. And in our situation, we're ponding it for more than 24 hours, which is above and beyond what the Ontario Building Code typically allows. We're using automated control valves or modulating control valves to release rainwater into the rainwater harvesting tank for reuse, or to gently release it as dry weather flow into the receiving storm sewer system. We're using logic controlled storage, so we're using programmable logic controllers, which we're going to talk about later. It allows for strategic and optimized water collection. So our tank in our basement is 5,000 liters, and we can store 60,000 liters on our roof. So before we installed the system, once our 5,000 liter tank filled, the rest of the water bypassed and went into the storm sewer system. But with this system, we're able to keep that water on the roof and use it as we see fit. So it's a very highly adaptable design. And we're excited to share some of those results with you today. And then just some high-level potential benefits of smart blue roofs that we're trying to estimate as part of this study is obviously peak flow reduction, which equates to flood reduction. What is the rainwater harvesting potential, notably for toilet flushing, irrigation? What are the evaporative cooling benefits of this type of technology when you allow that water to pond on the roof for prolonged periods of time during the hotter periods of the summer? What does that mean in terms of energy savings? What does it mean in terms of water conservation, in terms of how much water can we collect and use to offset potable water? And then finally, what are the utility cost savings? So with stormwater charge fees, with water costs, utilities, energy costs, what are those savings as a result of implementing this technology? So we're going to highlight on some of these benefits later on, but first I'm going to pass it over to Kyle to talk about this Blue Roof system overview.
Oh, thanks, Phil. Yeah, appreciate that. Yeah, so you're looking at the head office of Credit Valley Conservation in Mississauga. We have essentially two buildings there. We have the building in the back, and then we have the building in the front, which is Building A. And that is where we placed our Smart Blue Roof on it. You can see it is a flat roof, TPO, white TPO membrane. And so it was identified as kind of the ideal location for implementing a Smart Blue Roof. Next slide. So just to do a closer up of Building A's rooftop. So essentially what we did is we broke our roof into two zones. So zone one is where our kind of critical HVAC infrastructure is, where our outlet pipes are. And then zone two is our blue roof zone. And essentially within that blue roof zone, we have 4 drains with 2 emergency overflows identified in red there. We have 2 scuppers, and the entire size of that of the blue roof zone is 344 meters squared. So a fairly large area for that allows us to collect and store water on top of the roof. Next slide. So one of the things that we noted in the previous slide was a waterproof barrier wall. And so you can see that in the picture on the right-hand side is that barrier wall that kind of breaks or separates zone one, so it protects the critical HVAC infrastructure from water storage, and then zone two on the left-hand side of that barrier wall. And the picture on the left is kind of, looking out onto the blue roof zone. And there you can see, our drains right there. Our picture on the left, you can't really see. We have our monitoring infrastructure there now, but essentially this is where all of our water is being stored. Next slide. So one of the big considerations that we had to think about was how are we going to store that water on the roof in such a way there where we protect the integrity of the membrane. And during the construction process, we originally had a TPO, white TPO membrane, and we were installing a new roof drain for our Smart Blue Roof system. And we found that underneath, once we peeled back the membrane and we started getting into the insulation layers to install that new drain, we found that the insulation layers were wet, and that indicated a leak in the roof membrane. And so that put us on a path where we had to actually replace the roof membrane before the blue roof became fully operational. And so what we had to do was consider our different roof membrane options as part of the design process. And you can see that we had four options. We had a two-ply SBS mod bit roof. We had a single-ply TPO roof. We had a single-ply PVC key roof, and then we had a PMMA liquid applied roof, which is a polymethyl methacrylate
Acrylate.
based acrylic resin. So it was a liquid applied membrane. I still struggle with saying that word every time. But that was the identified preferred option was the PMMA liquid applied membrane, and in part is because it doesn't have any seams. So the reason why we wanted to go without any seams is because seams potentially offer a weak point in the roof membrane. And because we're storing up to, in certain areas, 25 centimeters or 250 mils of water, that would put quite a bit of pressure on our roof membrane and potentially create weak points in if there was like a seam that was part of our roof membrane. So we went with the liquid applied membrane, and underneath you can see that for each option we had an electric field vector mapping leak detection mat. And so that was our leak detection system. We had also 6 inches of insulation below that, and under there was the vapor retarder. But in particular, we also had an existing hollow core concrete deck. So we didn't add any kind of structural reinforcement. Part of this whole process and design process was to work within the existing structural load of the roof. And we wanted to make sure that with replacement of a new membrane, we're keeping everything kind of dry and protected. And that's really important for a hollow core concrete deck, because if you do get moisture in there, it can really create conditions that are unfavorable for the roof assembly. So the other thing too, we looked at how long are these roof membranes to last, and we saw that with option two, it could last up to 20 to 25 years. We did find with option three, when we had a TPO membrane applied, it only lasted, we were at the 12-year mark. Now, we weren't seeing leaks come through, say, into our third floor, but it gives you an indication of the lifespan of a TPO membrane. And we really wanted to maximize that given the conditions of storing water on that roof. Next slide. So here's just the application of the PMMA membrane. You see that the vapor retarder, and then you see them applying the liquid applied membrane, the PMMA membrane with a roller. Essentially, they did 2 coats. The first coat they put down, and then they put like a filter fabric adhesive to it, which would provide additional strength, and then they put on a secondary coat on top of that. Next slide. So this is the EFVM, electric field vector mapping, our leak detection system. You can see the steel mesh going down over the insulation that was being applied. And again, the whole intent of that is to, and we'll get into it the next slide, I believe, is to be able to detect problematic areas within our roof assembly quickly, and doing an inspection annually to check the integrity of our roof membrane. Next slide. Yeah. So essentially, this is how the system works. So what we do is we bring out, we hire a company to do an inspection of our roof membrane using the EFVM, and so they run a charge across the roof surface, and then they want to see if there's if that charge connects below to that steel grid. So if there is a potential leak and water is getting through it, that charge will come through. So they're actually wetting our roof surface while they're putting over across the roof membrane kind of a low voltage charge. And if it connects down to that steel mesh, then they're wired into that mesh, and then they'll read like an electrical charge on their meter. And so if they're reading any charges, essentially that could indicate a leak. So when they're close to the drains, you start seeing, because the water's moving down past that electrical steel grid, or past the steel grid, and you can see that they're reading a charge, but that's the water's going down through the drain. So we're okay there. But if they were reading it in other areas beyond kind of the drains, that would indicate there is a potential leak. And that allows us also to pinpoint where exactly it is so that we can reapply the PMMA liquid applied membrane. So it makes fixes a lot quicker. And so we're going to be running another leak detection test in November or December as part of our operations of the Smart Blue Roof. Next slide. So here's just kind of a cross section of the blue roof and how the drainage infrastructure works. So essentially, we have, as I mentioned, the 4 drains. We have the emergency overflow in the middle, and then the section that is highlighted in red. That's the modulating control valve. So that is what opens and closes the drain, and we'll have a close-up shot of that. But essentially, anytime that we're storing water on the roof, because we are complying with the Ontario Building Code, and which doesn't want us to have water stored for greater than 24 hours, which we are doing, and because we follow the CSA B805-18 rainwater harvesting standard, we have to mitigate our risk. And so we did a water safety plan of meeting that standard and meeting how we're going to address the Ontario Building Code. We had to put in a 3rd floor treatment system. And so we're cycling the water between the 3rd floor treatment system and the rooftop. So there is a suction line that is down at the far drain, which pulls the water to the 3rd floor treatment system, and then it pushes it onto the roof once it goes through both filters and UV light. If the water is drawn into the roof, that modulating control valve opens up, and that water through gravity drains down into our basement rainwater harvesting tank, which is approximately 5,000 liters. And then it goes through another treatment system before it is redistributed or reused to the first through 3rd floor bathrooms where we use the water to flush the toilets. So one last point is, we've noted 40,000 liters of rainwater storage. When we did get a kind of a post-construction survey, it actually can hold up to 60,000 liters. Next slide. So here's just a quick shot of the modulating control valve. So it is powered through electricity. So there we had, I think, Phil, that was your hand there that flicked on the power, and then it opens up when it's under power. But you can control it through our programmable logic controller. We can open and close it. So this is just a quick shot of the the system opening up from closed to open. But here you can also see in the picture on the left, the front pipe on the right-hand side, that is our suction line. So that is what's drawing our water from the pipe system, or the water that's being stored on the roof, and then it's moving that water to the 3rd floor treatment system as well. We also have cleanouts. You can see there's a cleanout drain at the bottom of our suction line as well. And there's also another valve that allows us to open and close that suction line to do maintenance work, to clean it out, to draw the water out, etc. Next slide. So we talked about that we are adhering to the CSA rainwater harvesting standard. So our system as a whole was designed to be the first Smart Blue Roof to meet that rainwater harvesting standard. And that outlays, so as a requirement of that, we had to do a water safety plan. And part of that water safety plan was to understand, okay, you're storing water on the roof. There's a chance for bacteria to grow within that water, that's being stored on the roof, and what are the risks to the people that that water may have contact with. And given that we are like an office space, there's potential for staff to come in contact with that water through aerosols. There's also the potential of that water, as we're using it for toilet flushing, for staff to come into contact with that water. So what does that mean? We have to have some kind of interventions, and then that's what that CSA standard identifies is what type of interventions do you need? Is it just mechanical filter? Is it mechanical filter and UV light? Is it mechanical filter UV light and chemical treatment through chlorine? So essentially, it lays out that standard based on the identified risk. And for us, it required both mechanical filter and UV light. And then I think we added chlorine on top of that as an additional cautionary procedure. Next slide, please. So here's the third floor mechanical room treatment system. So we have both a 20 micron filter in the picture in the middle, and then a 5 micron filter. And then we have the UV light on the picture on the right. And then we also have which we can turn on the pump, which essentially circulates the water from the rooftop to our third floor treatment system. We can do that manually, or we can do that through like an auto mode, where it's controlled by our programmable logic controller. Next slide. So once that water is cycled through those mechanical filters and through the UV light, then that water is pumped back onto the roof. We have two outlets essentially. And so that's how our system moves the water from the rooftop down through the floor and then back onto the roof. We have looked at ways of improving that circulation so that the water is stirred up and mixes better. And so we're looking at other ways to do that as well. Next slide. So when the water is drawn into the basement, which is our rainwater harvesting system, which essentially what it means is like we are now taking that water, we're reusing it for internal purposes. You can see there is kind of a main pipe that juts down. It does a bit of a bend. It goes over top of the main rainwater harvesting tank, and then it makes its way into, you can see in the kind of the picture, it says settling tank number 1, the picture in the front, or the tank in the front. And essentially we have 3 of those settling tanks. And that allows for kind of a primary treatment, allowing for any grit, any dirt, any organic matter to settle out of the water before it's moved into our main storage reservoir. So each of those settling tanks is about 1,000 liters. And then our main storage reservoir, as noted in the prior and in the title there, is 5,000 liters. Next slide. So here's just a shot of that water that, as it comes through, it's making its way into the settling tanks and then into the main reservoir. This gives you a sense of the water movement. We have butterfly valves on each of the tanks. We're able to shut a system down so that we could perform maintenance, but allowing, say, the 2 other settling tanks to still be in operation. Same thing with the rainwater harvesting tank. We can completely close that off, drain it, or clean it out as needed. We have the pipe infrastructure and the valves to open and close and isolate individual pieces of equipment. Next slide. So once we go from the settling tank, then it goes into first into 100 micrometer judo filter, which is kind of a self-cleaning filter, which is really handy because it does maintenance on its own for its own to keep it clean. And then it goes through a pump system, and then through, I think, is it 5 micron on that second one, Phil, or is that 20 micron after the judo?
It might be 5. Yeah.
Yeah, it goes to a 5 micron filter, and then it goes back through a UV light system, and then it goes into an agitator, And then at the point of the agitator, we actually add in a chlorine solution. You can see the chlorine pump. It's a peristaltic pump. So it essentially adds a certain volume of chlorine and a water mix into the system as it's being agitated. And then it comes back up and out and then into our gray water line, which then is used for flushing toilets. One of the things that we've learned here is trying to figure out how much do we pressurize the line, because we're in the basement, but we have to move the water not just to the first floor, but the second floor and the third floor. And we have to have enough pressure at the toilets to make sure that they flush properly. But we've had to be really cognizant of how much pressure we can put into the system. So with this UV lamp in particular, we can only pressurize the line up to, I think the max is 125 pounds per square inch. And so we essentially can pressurize the line up to 120 pounds. We don't go all the way, but that gives us enough pressure to ensure that each of the bathrooms, the toilets are flushing properly. And we've received plenty of calls on that when we've had toilet flushing issues. So it's been a process of learning to get the system right. Next slide. Oh yeah. So this is always like a good check for us, is like, okay, do we have enough power? It's kind of funny. Like I never thought this is what we would be focusing on, but it is something when you get into the operations of this becomes critically important, because it becomes, if it's not flushing properly, you're going to have issues with your colleagues.
From the operation perspective, we started this system in May of 2024. Per our building permit, the system operation is during the warm months, so that's May 1st to October 31st. And then during the cold winter months, that's when the system is shut down. We still harvest rainwater. It moves from an active system to more of a passive system. So we have the next slide. So as Kyle was talking about, we have a programmable logic controller, and this is really the brains of the system. So you have inputs like temperature sensors, water level sensors, and you have outputs such as controls to open and close valves, to turn pumps off and on. So if you go to the next slide, I think there's a schematic that kind of shows that. Yeah. So the PLC, again, it's the brains. So that the sensors on the roof that measure temperature and water level tell the PLC, okay, how much water is on the roof? How much water is in the tank? Do we want to fill up the tank? And if it does, then the PLC will then open the valves, which will gently allow that water to come down into the tank. And then the water level sensor will be real time telling the PLC, okay, I'm full, close the valves and keep the rest of the water on the roof. So that logic system is really powerful in terms of adaptable, optimized infrastructure. And another component to this is the data is collected on a 5-minute time step, and it's sent into a data sphere. And then from the data sphere, it's sent into a whiskey database. So we can take all that data that's collected on a 5-minute time step, and we can calculate key performance indicators, because trying to manage this data in Excel is impossible because of the size of the file. So working with a database like Whiskey is going to give us the ability to manipulate and work with the data and calculate some of the key performance indicators. Next slide. This is just an example of an input, an ultrasonic level sensor that's constantly measuring water levels on the roof, water levels in the tank, and of course temperatures of the roof membrane, and then even temperatures underneath the concrete slab core roof, to kind of understanding what the temperature differential is during different times of the day, weeks, and months. Next slide. And then the modulating control valve, as Kyle said, it allows us to have precise flow control, and it allows us to more of a dynamic release. And I got a little video I'll show you of a dry weather release flow rate, just so you can kind of see how we can gently release the water from the roof. And it's also a butterfly valve, so it fails open. And in retrospect, we're starting to realize that failing open isn't the best actual solution. having it fail closed would have been better for a number of different reasons, but we can get into later. Next slide. This is the human machine interface on the PLC. So on the left is like the roof dashboard. And again, it's those inputs like water level. So it's telling us what the water level on the roof are, and other inputs such as temperature. And you can see there's like active zone 2, active zone 1, outside air temperature, attic roof temperature. So these are live dashboards that show you what the real-time information that's coming into the PLC. And then on the right is kind of an example of inputs and outputs. So it tells you what pumps are running, what valves are open and closed, that type of thing. So it's the human machine interface is a great piece of the equipment as well, because it gives you a snapshot of what the system's doing. It tells you what the alerts are or things you might need to change if there's faults. Next slide. I think this might be the video of the dry weather release. So this is showing you those modulating control valves when they're open and allowing water to be released as dry weather flow. So here the valves might be maybe 5 or 10% open, but you can see you get that gentle release of water into the storm sewer system. It's not a surge or a massive amount of water at once. We can allow it to trickle and almost replicate like a base flow from a wetland. So it's a really great advantage to this, because in some cases you can release water over a period of an hour or two, gently releasing it into the adjacent storm sewer system. Next slide. And then, yeah, I've already touched on cost. I think I'll move into the public health results, Kyle, just because we only got 15 minutes.
Yeah, so we did conduct some public health research. And so one of the things that we have to, when we think about public health, there hasn't been a lot of public health research done in relationship to kind of stormwater management features. We've kind of touched on the fringe of it, where like, what are the benefits of green infrastructure to like general populations, with COVID. Access to green space obviously became very important. But we haven't looked at, okay, what are the bacterial levels? What is the associated risk? When you look at kind of some of the water quality criteria, there's obviously the enhanced water quality treatment from MECP, which focuses on TSS, or total suspended solid removal. And so if you have, say, 80% reduction, if you from the inlet of your stormwater management practice to the outlet of it, it's meeting that enhanced water quality treatment criteria. Lake Simcoe has obviously phosphorus removal, and they use, LID and source and conveyance controls and other features to do that. Swim ponds as well to help and aid removal of phosphorus, but that is kind of geographically kind of local to that particular area. That phosphorus removal doesn't account for say swim design criteria within CVC's jurisdiction, for example. And there's no, when we looked at criteria for bacterial levels, there is that for potentially for water reuse, but it's not necessarily in relationship to stormwater management facilities as to how do you manage and operate these facilities and maintain, minimal risk in terms of bacteria. So what were some of the drivers? Well, for public health monitoring, well, really they're unknown. For storing rooftop water, we didn't know, we knew bacteria would grow on the roof if we were storing water on it, but we don't know what type of bacteria, how much, what are the bacterial counts? And we were one of the first smart blue roofs in Canada. There's only 2 known smart blue roofs, one that exists in Elmira, and that was our kind of design consultant who did that on their own roof. And then we have ours in Mississauga. And as I noted before, meeting that rainwater harvesting standard that CSA produced, identifies exposure risk from rooftop storage and reuse. But what exactly is that? And are we creating some level of risk when we're just leaving water stored on the rooftop, but without receiving any form of treatment or intervention? And so as I noted before, we have a relationship with Toronto Metropolitan University. We have this is Dima Balal. She is a PhD student. She in public health, and so she put forward kind of a design monitoring a design for a monitoring program that would measure bacteria levels on the rooftop. And so, the ones that we were focusing in particular were E. coli and Legionella. And we also we'll show total bacterial counts as well in terms of what we were seeing on top of the roof. And so this was also selected based on like, why did we focus on E. coli? Well, E. coli are often used for public beaches. They're often used they also have requirements for irrigation. And so we wanted to see, where our levels were at and how would our mitigation factors impact fecal coliform levels. So like when you're thinking about irrigation, you should have fewer than 100 bacteria per 100 milliliters of water. In terms of total coliforms, you should have fewer than 1,000 bacteria per 100 milliliters of water. So there's some criteria, but doesn't necessarily fit in terms of stormwater management. Other things that we could look at is BOD, TSS, turbidity, again, E. coli, and total chlorine residual and stuff. So this was particularly for toilet flushing and urinal flushing within our office space. What should our levels be? So we knew that we had to have, at least when for our basement treatment, we had to have a residual of 0.5 milligrams or greater, essentially, in terms of chlorine residual within our pipe system. Legionella, again, like it depends on what Dima kind of explained to CBC and to us was the fact that Legionella is very airborne. And so given that we're storing water on the roof, if we say have office windows, we want to make sure that we're mitigating any potential risk of that aerosols making their way into our office HVAC system. One of the factors that we also employed was redirecting the air intake. So instead of pointing towards our blue roof system, we're actually pointing in the opposite direction, and we extended our air intake about 6 to 7 feet so that it's on the very opposite end of our rooftop in zone 1. But you can see, okay, at what levels does it correspond, a certain degree of risk, and also in terms of disinfection of any system. So when we looked at, we say water quality and so smart blue roof, and this was a composite sample. And so we were looking at total bacteria levels. And so, we did samples in both 2024 and 2025. We kind of struggled with getting on top of our chlorine. We were applying liquid chlorine in 2024, and then we switched to kind of solid chlorine pucks for 2025. And we used, I think it was calcium chloride was what we were using, right? In terms of the pucks that we were selecting. And these were kind of long-lasting pucks. So they had kind of a residual, they had a staying power that we weren't kind of experiencing with liquid chlorine. And we used essentially pool floats. So essentially what ended up happening is we began managing our blue roof more and more like a pool, and we're using some of the equipment that you could buy for a pool. And you can see in red, this is our bacterial count, our total bacteria count. We're looking at 23,100 total bacteria count. And the reason why it was so high, because we had a chlorine residual of 0.13. So this was at the beginning of July, right after July 1st. And then, staff were off on that day. So, and that corresponded to a high bacterial count early in the morning. And then as we brought that chlorine residual up to 0.65, which all of our chlorine residual is in blue, you can see that all of a sudden our bacterial count drops down to 25. And then we keep it up around 1, between 1 and 2, or total bacterial count drops significantly. Again, when we have it down at 0.16, so the chlorine levels drop, we start to see that incremental rise in bacteria counts. And then as we were more consistent with our chlorine levels overall, you can see our total bacteria counts were very minimal, like 6, 2, 0, 0, 0. Again, it got a little bit low probably over the weekend. Maybe it was a holiday weekend. And then our bacteria counts got up to 100, and then it slowly dissipated, so that by pretty much the end of the year, we were all around, 5 or less. Six was the highest number, and that was from August 13th to essentially August 20th, that last week of sampling. So we know as long as we keep our chlorine residual up, we can really control our bacterial count. And this rang true also for E. coli. You can see our counts getting high. And, this E. coli can get generated from any kind of debris, organic matter, uh, bird droppings, etc. Start creating that environment. So, but you can see though that as we got later in the year, when we were kind of more, we were at 0.03, 0.04. That's when we have these spikes. But as soon as we start getting more consistent with our chlorine levels, as you can see in the latter half, then our E. coli drops down to 0. So minimal amounts. We were using kind of 1,000 CFUs per 100 mils as our criteria. So we never exceeded it. So we got better and better as the summer progressed, and we found chlorine to be an effective intervention in keeping E. coli levels down, if not 0. With Legionella, the same thing, got a little bit high here, but it was when chlorine was particularly low. And so as chlorine levels came up, again, the bacterial counts came down and were minimized to 0. So again, that falls in line with what we saw with total bacteria, with E. coli, and then also with Legionella. So just the impact, without chemical treatment, it is difficult to mitigate bacterial growth with rooftops water storage. Even when you're running it through those mechanical filters, yeah, they can cut it down in terms of the amount of organic matter that is kind of within the water that creates those conditions for bacteria. You can run it through a UV light and it does it, but it's like, I always say it's like, pouring water into chicken soup. Once bacteria is established on the blue roof, it doesn't matter if you run it through the filter in the UV light. It may help a little bit, but it's going back into an environment that is kind of bacterial rich. So chlorine does that job of killing the bacteria on the rooftop so that when you filter it, when you bring it through UV light, it's not going back into dirty water. So that's what we really found helpful, was that chlorine had a huge impact on managing our bacteria levels and mitigating any public health risks from blue roof systems. Phil, I'll turn it back to you.
All right, thank you, Kyle. Next slide. So as I mentioned earlier in the presentation, in July of 2024, Mississauga and parts of the GTA got hit by some pretty large storms. And you can see on the right, it might be difficult to read, but I'll explain it. The rainfall depth variability across Mississauga was pretty extreme. But you can see the red dots represent rainfall amounts that were greater than the 100-year storm. So that resulted in a lot of the infrastructure becoming overwhelmed. That resulted in all that flooding pictures I showed earlier of cars stranded, of people getting rescued from nursing homes and such. If you go to the next slide, there's the August 18th storm, which it actually had even larger amounts, 170 millimeters of rainfall in some areas. So we were really fortunate last year to have the blue roof up and running, because we really got to stress test our system to see how well it could perform in historic flood events like we experienced last year. Next slide. So this is just a quick video of the roof on July 16th. I don't know if it will play or not, Kyle. There we go. This is us. On July 8th, we had Hurricane Beryl come through, and we captured that amount. And then on July 16th, we had another deluge of rain that we were able to stack. So we were able to catch one storm and then stack another storm on top. And what this really is telling us is that for these extreme rainfall events, we're able to capture every drop of water and not release anything. So with the July 8th and the July 16th storm event, we were able to capture the water, and we still had freeboard for more. So it just goes to show how much capacity these flat roofs have. When you factor in the structural capacity of them, they can hold a lot of water. So if you go to the next slide, it kind of summarizes the two. So July 8th and July 16th combined had 122 millimeters of rain. We captured all of it. And then again on August 18th, we captured another 83 millimeters of rain, captured all of it. So that is 100% peak flow control. And when you think about municipalities, there's not a lot of space in the public realm to store or to capture the water. So it just goes to show how private side infrastructure could play a really important role in terms of managing stormwater. So when I showed those images earlier of all those flat roofs, that is a major untapped flood control infrastructure that has a real potential to make a significant impact on downstream drainage. So if you go to the next slide. So this is just, I mentioned this already in the Q&A period, but over a certain length of time, August 18th to September 6th, we saw that we were able to lose 50% of the volume to evaporation. 42% was harvested for flushing toilets, and then we just had a minimal amount released as dry weather flow. And up until yesterday, when you look at the total amount of water that's been used to flush toilets, and you look at the fraction that was used based on potable water and the fraction for the rainwater harvesting amount, we've got about a 60% offset of potable water use, which is quite remarkable. And that's during the operating season of the Blue Roof and when it's off during the colder periods of the year when it's more of a passive system. But it's exceeded our performance. We were hoping for 40%, and we've achieved 60%. Next slide. So as I mentioned in the Q&A period, we're thinking about how do we scale this up from the site scale to the street scale to the neighborhood scale, and what kind of impacts can we have? So if we go to the next slide, it'll take us to the street scale. This is a neighborhood in Mississauga where we looked at building footprints that were very similar to the building footprints at our head office. And this system has a storm sewer that was built in the early 1980s. It was designed to convey the 10-year storm event based on a runoff coefficient of 0.6. When you look at the current impervious surface today, it's about 0.8, which means that storm sewer system is undersized for the 10-year storm. So if it's only got 40 years, it's only 40 years old, but it's already no longer providing the level of service that it was originally designed to do. So the municipality has a decision, do we upsize the pipe, or could we, if you go to the next slide, retrofit that street with blue roofs, so that you could kind of get a sense of, yes, what option is to upsize that storm pipe, or maybe we can retrofit and restore the capacity of the pipe and extend its useful life. So that's really looking at the life cycle of the infrastructure. So if you go to the next slide, we created this animation that kind of explains it. So there's the design flow for the 10-year storm based on conditions in the early 80s. The next flow is current conditions based on the current imperviousness, because we know that imperviousness often grows. Areas, parking lots get expanded, or additions get added on. So the imperviousness of the catchment increased significantly from when it was first designed in the early 80s. Then we looked at, okay, if we took all those flat roofs and we put on blue roofs based on the performance we measured at our head office, we could actually throttle the flow back to 2.58 cubic meters per second and get restored capacity. So by doing that, we extended the lifespan of our pipe by 40 to 50 years, if not longer. Then we also looked at climate change. If we factored in climate change, it's slightly surcharged, but it still provides that infrastructure resilience to future extreme storm events. So from a performance, a technical performance perspective, at a street level, it performs very well. Now let's look at the neighborhood scale. So this is, we developed a PC swim model, there was a PC swim model developed for the headwaters of the Cooksville watershed. And we took that model and we modified it to see what it would look like if we added blue roofs across that catchment. So if you go to the next slide, it kind of gives you a visual of that same catchment. What would it look like if we took all those roofs and we stored different volumes of water on the, or different water depths on the surface? What would it mean to the downstream end of the drainage system? So the first slide shows you, sorry, Kyle, next slide. This is existing conditions. So on July 16th, there's what we saw on one of the roads at the bottom of that catchment area. The major system was active. The full right-of-way was flooded, and you can see there's a car stranded in the middle of the water there. So what we wanted to understand was, okay, how would our conditions improve as we stored incremental amounts of water on those flat roofs I showed in the previous slide? So if we go to the next slide, just capturing 50 millimeters resulted in a peak flow reduction of about 14% and a total volume reduction of 15%. So just to conceptualize what that would mean, that's about almost 30 Olympic-sized swimming pools. So that would take that water out of the system and potentially lower those floodwaters that we saw on Matheson Boulevard, as well as floodwaters downstream of this catchment. Again, when we look at 75 millimeters, I'll try and pick it up because I know we're almost finished. We saw a reduction of almost 20% in peak flow reduction, and we saw a volume reduction of 20%. And that's 43 Olympic-sized swimming pools that we removed. And then if you go to the next slide, 119 millimeters. Now, we know we could store more than 119 millimeters, but the 100-year storm rainfall depth is only 119 millimeters, so you can't store more than what actually falls. But here we were able to capture 64 Olympic-sized swimming pools, and we had, almost a 35% reduction in volume. So when you go to the next slide, as I talked about, what we're going to be looking at next year is taking the outputs of this PC swim model and actually trying to compute what would the reduction in flood lines or water levels look like in this particular area and downstream, and what would that mean in terms of reductions to damage reductions, whether it be flooded buildings, whether it be erosion damage to infrastructure. And it's a very difficult thing to calculate, but we're going to give it a shot. But we've got we're very data rich now. We've got really great data at the site scale. We can now scale it up to the neighborhood scale. And we got some really great tools at our disposal, such as the risk and return on investment tool. So stay tuned as we work through those numbers. And then finally, I'll just end it with tours. I know this was a virtual session, but we always welcome people from the industry that want to learn more about this technology, where we can bring you in and we can show you the roof. We can show you the modulating control valves. We can bring you down to the basement and show you where all the infrastructure is and how it works. So with that, I'll leave it there. I think we're almost out of time, but yeah, if there's any quick questions, we'd be happy to answer them.